Okay, Spain, afternoon. Hey, Yago, good afternoon. Okay, so I think Kayla or Daniel, you can look at the waiting room and invite or accept people. Okay, so because it's
Yeah,
already 11, I'll start with my discussion. Hi, Sanjay. Okay,
yeah.
per
I'm in, and also Kayla is um, checking it.
okay, perfect. So all of you can see me, you can hear me. So today is the last part, is the last concluding part. We started off with laying out what the problem we are trying to solve. The problem is core CT scans, and we want to generate in situ mechanical logs. We have very high resolution in for the CT scans because they are captured in the lab. So this very high resolution, and we have very low resolution in situ logs. We want to map, we want to understand the relationship. So what I've told you so far is what we are trying to do. And for this particular task, what is the most important thing is you have all those CT scans, high resolution CT scans. You have to first extract features. You have to extract features from these CT scans so that you can then relate the features to the target. And for us, the target is geomechanical, which is Poisson's ratio, bulk density, porosity, and so on. We are not predicting any permeability. It's very difficult, but I have mentioned it there because that was one of the tasks that we wanted to try and see. In academia, we can try a lot of interesting ideas. Some of the ideas will work and some of them will fail. That's perfectly fine. Okay, uh, so I'll quickly go through the slides that I have already discussed. I will not spend a lot of time. I'll just go one by one so that you kind of know what we have been discussing. So synthetic geomechanical logs from CT scan. This is CT scan. We have CT scan measurements on the cores, very high resolution. We want to generate the targets. These are geomechanical properties in the subsurface in situ. We also have feature set 2. Output, we have only 181 samples for this demonstration. There are, when we did it in a real world, we need more samples. Okay, so for purposes of demonstration, we just have 181 samples. So the method that we are using to understand this relationship is data driven. And when you do data driven, the first thing is you have to perform exploratory data analysis. And in exploratory data analysis, you first try to understand relationships between each feature, relationship between the feature and the target. You can do a lot of different things. All this thing belongs to pre-processing. You have to explore the data, you have to pre-process and ensure that your data is clean and ensure that your data-driven workflow honors what you learned from. So in the workflow, we have 4 steps. Today, let me discuss these 4 steps because I have not discussed these 4 steps. And in most of my data-driven work, I generally use these steps. Okay, so they tend to work well, and you can follow these steps for any data-driven workflow. So step number 1 is you have to compile. So I don't know who is muting me and why. Maybe it's Kayla or Daniel. I'm getting muted. Okay, so the first step is
Yeah,
data set. You have to collect your data set, right? In this case, our data set has logs that we want to predict. It has CT scan images, and there are some CT-derived properties. Then we have to perform pre-processing. In pre-processing, first you need to remove bad data. So this is what we are doing here. We are removing bad data. You have to make your data suitable for your task. In my case, I had to remove the outer edges. I have discussed all that last time. Then you have to create features. I create two types of features, one from the CT scan images. There are 214 features. And then I have feature set 2, which is 35 features from the 7 CT-derived properties. Today, I'll continue from feature extraction. After feature extraction, what we need to do. In the last discussion, I spent a lot of time on how to create feature set 1. So creating features is important. You cannot do anything with the raw data, right? So raw data needs to be converted into features, and then you can use data-driven models to relate it to target, to find the function that relates the features to the target. That can be done only after feature extraction. Now, because I'm using only 180 samples, I need to perform multiple train test split. Today, I'll also show you multiple train test split. Going ahead, once you create your feature, then always remember you have to standardize the feature. You have to scale the features. What is scaling? If you have two features, feature 1 and feature 2, if one feature goes from 0 to 1, it always stays between 0 to 1. The other goes from -100 to 100. These two features have different scale. So you have to bring all those to a similar scale, and that is very important. So always remember to scale your data. Training data set contains the features that you extracted, right? So you scale the data and then you reduce the dimensionality of data. What do I mean by dimensionality of data? If you have 100 features, if you develop a data-driven model to relate 100 features to a target, you can do that. Data-driven models can always relate large number of features with a target. It is very easy to do that. That is called overfitting. If you give it a lot of features, it is very easy to relate anything. So you need to perform dimensionality reduction. What I mean by dimensionality reduction is you need to find which of these 100 features are important for your task. You can only use, let's say, 15 or 20 features. There's no rule of how many features there should be. But for traditional data-driven workflow, for traditional machine learning, where you have limited number of data, limited number of samples, you need to have limited number of features. So you cannot use all the 100 features. You just need, let's say, 15 features. So you have to find 15 important features out of those 100. And now when you reduce the number of features, it will be harder to relate to the target, but you will not overfit. Overfitting is a problem. What do I mean by overfitting? Overfitting means that you will perform very well on the training data. You will perform okay on the testing data, but your future deployment will be very bad. So that is overfitting. And the reason, there are two main reasons why you overfit, and you have to be careful. There are two main reasons. One is using large, or sorry, using lot of features. If you have too many features, you will overfit. You don't want overfitting. Overfitting means you will not perform well on the new data that the model has never seen. So if you have a lot of features, you will tend to overfit. The second one is if you use complex models. You can only use complex models if you have a lot of data, if you have a lot of samples, right? If you don't have a lot of samples, don't use complex models. If you use complex models, you will overfit. So we have to ensure that we don't overfit. That's why immediately after scaling, I perform dimensionality reduction. Okay. Now here, you can perform outlier detection, which I have not performed. And there's something called feature transformation, which I have not performed for this particular task. Each feature has a distribution. What you want is the distribution to look like a Gaussian. A lot of data-driven methods work well when you have a Gaussian distribution. So that's why feature transformation is important. And what I would recommend is to perform feature transformation before scaling. It is my recommendation. A lot of, for example, standard scaling assumes that your feature is Gaussian in distribution. So you need to remove outliers, perform feature transformation, and then perform scaling. Now coming to dimensionality reduction. Why? Because you want to reduce overfitting. And for dimensionality reduction, the first thing I'll do is I'll remove features. Yeah, I think I did a mistake here. Let me think. Yeah, I did a mistake here. So you have features, a lot of features, and then you have a target. What you need to do is, if the relationship between the feature and the target is not strong, relationship can be linear, it can be non-linear, but you have to find different ways to quantify that relationship. How strong is one feature with respect to the target? There are a lot of different ways in which you can quantify the strength. So the first thing is to reduce the dimensionality. You have to remove features that are not linearly correlated. There's no strong linear relationship. Remove features that are not non-linearly correlated with the target. So anything that doesn't have correlation, remove those features. Those features are useless. Those features don't explain the target. And after that, you have to remove highly correlated feature. What I mean by that is, if you have feature 1 and feature 2, if feature 1 is twice feature 2, 2 times feature 2, then don't use feature 2. Just use feature 1. So if something is 2 times feature 2, or if F3 and F1, they are related like this. F1 is 3 times F3 plus 10. Don't use F3. Reduce all these features, remove all these features. So you remove highly correlated feature. And when I say highly correlated features, it's generally the linear relationship. You don't want F1 and F2 to be linearly correlated. There can be non-linear correlation. There's nothing wrong with that, but linear correlation, try to remove. And at the end, if there's a feature which doesn't have enough variance, remove that. What I mean by that is, there is a feature that changes a lot. This is the distribution of the feature. And then there is another feature, which is something like this. There's a high distribution, a lot of variance for feature 1. There is very small variance for feature 2. Then remove feature 2 because it doesn't have enough change. So why to keep it there? Keep something that shows enough change so that your model can learn how to relate those changes to the target. Any questions on this? Dimensionality reduction, very important. Outlier detection, which I have not shown. Feature transformation, which I have not shown. And then scaling, and then dimensionality reduction. In dimensionality reduction, I did a mistake, which is I forgot to put that not. You're removing features that are not related to the target. So by doing all that, what you end up with is a dimensionally reduced training data set. Okay, dimensionally reduced, a much smaller data set. And just to remind you, this is something that's a lot of you who are new will get confused, is there is something called size of the data and dimensionality of the data. So only for those who are new. So size of the data, what I mean by size is how many samples are there in the data. If there are 100 samples, then the size of the data is 100. If there's 1,000, there are 1,000 samples. A big data or A large size data will be something with where there are 1 million, 10 million samples. So size means number of samples, and dimensionality is the number of features you have for each sample. If you have 10 features, it's a small dimension. If you have 1,000 features, there can be chance. It's a very high dimension data. You have to reduce the dimension. And in each data set, your goal is to relate those features with targets. You can have one target or multiple targets. If there are no questions here, I'll just move ahead. So remember, I showed you the workflow. Step one, you create your training data set. Step two, you pre-process your training data set. Now, this is something very important, which those of you who are new, you will forget. And when you forget this step three, what happens is you will get a very good score. You will get a very good performance, but that's not the reality. So this workflow number 3 that I'm showing you here is important. So any pre-processing that you do on the training data set, any pre-processing that you do on the training data set needs to be done on the testing data set. But it has to be done in a particular way. What I mean by that is you will learn how to scale. You will learn how to scale on training data. You will learn how to reduce features on training data. You will learn all this thing from training data. You will learn how to detect outliers. You will learn how to transform the features. Once you learn all that on the training data, whatever you learn needs to be applied on the testing data. You're not learning from testing data. You're applying whatever you have learned from the training data on the testing data. I always recommend that whenever you do any data-driven model, the first thing you should do is you should split the data into training and testing right at the beginning. And then whatever you do on training needs to be done on testing. But it has to be done in a particular way. What I mean by that is so for example, standard scaling. In standard scaling, what you learn is the mean of a feature. Sorry. You learn what is the mean, which is average, and you also learn the standard deviation from the training data. Then you will apply the mean and standard deviation on the testing data to get the scaled data. You don't learn it from test data. So it is something very important that you need to always remember. If you don't do that, then you will get a pretty good score, but that is unreliable. One important rule is treat test data as new unseen data. Don't do anything on the test data which you cannot do on any data that you have not seen. So always treat your test data as something that is new, unseen. So after scaling training data in workflow 3, I'm scaling and reducing dimension of testing data. Any questions on this? So after all that hard work, you develop the model. I always mention that developing model will take only 20% of your time. What is more time consuming is preparing your data 40% of your time, and then evaluating, trying to understand whether your model is good or not, testing it, validating it, and so on. So model development is only 20%. There are so many different models. Understand the assumptions of each model and use the model that suits your data. You cannot use any type of, and again, you have to decide whether you want to use complex model or a simple model. If the size of the data is small, then use simple model. Don't use complex model. When you develop your model, in my case, I have to perform downscaling. What I mean by downscaling is I have features which are very high resolution. I reduce the resolution of the features to low resolution. What I mean by low resolution is 0.5, 1 sample per 0.5 feet. The high resolution, I had one sample per 0.002 feet. So from that high resolution, I need to downscale. Why do I need to downscale? Because my target is the bottleneck. Target also has a resolution of one sample per zero point 0.5 feet. Okay, so I have to perform downscaling. After downscaling, whenever you develop your model, always you have to perform these two: cross validation followed by hyper parameter optimization. I'll explain what these two things are later on. Once your model is developed, the performance on the training data is called memorization performance. It is very easy to get memorization of, let's say, 95%, a very good score. It's very easy to have a high memorization. If you are if you're not careful to avoid overfitting, then you will get a very, very good memorization. So memorization is what you get on the training data. It is not important. Generally, you will always get a very high training score or a memorization score. What is important is how you perform on testing data. If there is overfitting, your testing performance will be 60% or lower, and your memorization performance will be very high. So that is a warning, that is a caution that you are overfitting. Either you have too complex of a model or you have too many features. So you either need to reduce the number of features or you need to use simpler and simpler model. You always need to monitor overfitting. Once you find a model that gives you a good memorization score and a good testing score or a testing performance, which is called generalization performance, then you're ready to deploy the model. Okay. Any questions so far on the workflow? I showed you data cleaning. I'll skip these. We have already discussed cleaning. We have already discussed feature transformation. We spent a lot of time on this. Okay, so now I'll tell you, what do I do after feature extraction, right? I showed you feature extraction. Let's see if there is something on the chat. I see two things glowing. Is there any rule of thumb for minimum score for generalization? So generalization is testing performance, and there is no rule of thumb. Why? Because there is no one way of measuring performance. You can use mean absolute error. You can use root mean square error. You can use R square. There are so many different ways in which you can quantify performance. But the takeaway is there shouldn't be a big difference between training and testing performance. And your training performance should be good, which is very easy. It's very easy to get a very good training score, memorization performance. If your memorization performance is not good, what it means is your data is not suitable for your task. There's no relationship. That's why your memorization is not good. There's another question: outlier detection by wavelet transform, dimensions reduction, principal component analysis. So a lot of you will use principal component analysis for reducing dimensions. I generally don't use principal component analysis. There are two reasons why I don't use principal component analysis. Reason number one is if you perform principal component analysis, you're combining your features. What I mean by that is you lose the physical meaning of the feature because now you're combining the features. So that's one reason why I don't use a lot of principal component analysis, but that is a smaller problem. The bigger problem is if I want to do classification, then principal component analysis, to the best of my knowledge, is not a good technique. Uh, what it does is it kind of mixes the groups together. So that's why I don't use principal component analysis for reducing features. I use this workflow that I showed you. I look at relationships, I look at collinearity. If I need to reduce it further, then yes, I may need to use principal component analysis. In this case, I'm not using it. Okay, so just to remind you, I have CT scan image, high resolution. Let me go back. High resolution. I perform feature extraction, but I don't perform feature extraction uh, blindly. What I do is I collect all the useful slices over 0.5 feet. Why 0.5 feet? Because my target is one sample per 0.5 feet, but my feature is one sample every 0.002 feet. So it's a very high resolution. I had 44,000 samples. Out of that, 33,000 samples were useful, and I collect all the useful samples every 0.5 feet. Then I perform feature extraction for each zone. I call it zone. It is divided into 0.5 feet zones. When I perform feature extraction, each pixel in that image, in that slice, is assigned a value. It's a number, right? So because it's a number, for each zone, I can get a feature distribution. For each 0.5 feet, for each feature, I can get a distribution. Then what do? Then I look at simple statistics. These are simple statistical parameter for each region in the distribution. So I divide this entire distribution for the entire sample, 90 feet of sample. I divide it into 6 zones. For each zone, I am extracting statistical parameters. So by doing that, what happens is pixel intensity is generating 55 features. So for example, 1, 2, 3, 4, 5, 6, right? So there are 6 statistical parameters, and I divide it into bands. And based on how many bands I have for each feature, I get different number of features per feature extraction method. So based on pixel intensity, I have 55 features. Based on Sobel edge detector, I have 57. Based on LBP, I have 36 features. On wavelet, 33, Asian 33. So overall, I have 214 features per zone. These features have some meaning. Why they have some meaning? Because it's a statistical transformation of feature distribution which were obtained after feature extraction. So all these 214 features have some physical or mathematical meaning. Remember, there were 2 feature set. One is from CT scan image. The other is CT-derived properties. For each CT-derived properties, I look at 0.5 feet zone. For 0.5 feet zone, each CT-derived property has a feature distribution. I divide the feature distributions into bands, and I extract statistical parameters. So by doing that, for each feature, I'm having 7 statistical parameters. Sorry, for each feature, I have 5 statistical parameters, and there are 7 CT-derived properties. So at the end, I have 35 features coming out of CT-derived properties. So this is feature set 2. Dimensionality reduction. I showed you the method, right? So based on the method, first I look for strong relationships. Which of the features have strong relationships with the target? What you're seeing here is 214. Wait a second. Yeah, 214 features for, and the relationship with the target. I'm interested in only these features which have high strength. These are low strength features, low strength, low strength. I don't need these features, so I remove them. And what you're seeing here is the relationship. This is a linear relationship. How strong is the feature linearly related with the target? And the target that I'm looking at here is Poisson's horizontal. Because there are 4 targets, here what you're doing is you're looking at relationship with effective porosity. When it comes to effective porosity, this zone is not strongly related. These zones are strongly related. So what you see is similar patterns. So when it comes to features, features are almost the same in terms of relationship with the target, which is Poisson's horizontal, and with effective porosity. So 43% of the features have more than 0.5 correlation coefficient. 37% of the features have more than 0.5 correlation. So I'm looking at the strength. There are very few which have strong relationship. That was on feature set 1. On feature set 2, which has 35 features, I see that there are very few that have strong relationships. So I don't need all the 35 features. Here I'm looking at linear relationship. I also look at non-linear relationship. I also look at collinearity. Okay, I'm not showing you everything. So by doing these 4 feature reduction steps, 4 dimensionality reduction steps, I reduce feature set 1 from 214 to 119 to 57 to 29. So this 29 is the final features that I'm left with. So from 214, I reduced it to 29. I can work with these 29 features. I will not be overfitting. For feature set 2, I had 35 features. I reduce it to 6. So instead of working with 35 features, I reduce it to only 6. Any questions? Okay, it's pretty important. Now, if you want to understand relationships between feature and target, in sklearn, there is a module called F-test. It will tell you how strongly is feature related to the target in linear fashion. It is showing you linear strength in relationship. You also need to look at mutual information, which is telling you non-linear strength between feature and target. You need to look at both linear and non-linear. Okay, now it's time for me to show you the performance. Okay, so now it's time for performance. It's very easy to generate results, but it's very difficult to pre-process and clean the data. That's what I want to emphasize. So right now we are in the model development phase. I will downscale, which I've already shown you. I'm downscaling it to 0.5 feet zones. And when I develop the model, I'll always perform cross-validation and hyperparameter optimization. Let me show you how I do that. Because I have only 180 samples, plenty of times you'll have only 180, 200, 500 samples, not more than that. When you have so little data, when you train your model should see everything in the data. Because such a small data, you have to see all the statistical patterns in the data. To ensure that, what I've done is I have splitted randomly the data into 5 splits. This is not cross-validation. Those of you who know what cross-validation is, this is not cross-validation. Even before cross-validation, I divide the data into 5 splits. What you see here is 90 feet of data. I'm dividing it into training and testing such that testing data is always continuous. There's no random sampling. It is a continuous data. We want to preserve the relationships of geology. In subsurface, things are related in depth. So I keep the training data, the testing data continuous. By keeping the testing data continuous, the training data is also continuous. This is one of the things that helps me anytime I work with subsurface data. I don't make it random. Because I have a small data, I'm dividing it into 5 splits. If I'm developing a good data-driven model, then the performance on split 1, split 2, split 3, split 4, and split 5 all should be good if I'm developing a good model. If the model is weak, it will not perform well on each split. This is called multiple train test split, and this is done because of compulsion, because I don't have enough data. I want the model to see all the patterns in the data. I don't want to miss any pattern, and I want to test the model on each pattern in the data. At the end, data-driven model is all about seeing statistical patterns in your data. So this is multiple train test split. Now, on each training data that I have in this 5 splits, for each training data, I perform cross-validation. So those of you who are slightly knowledgeable of data-driven method, you know what cross-validation is. What is cross-validation? I have a training data. I will divide the training data into 3 folds. So when I train the model, first I'll train the model on this fold and validate the model on this. Next, in the next fold, I'll train it on the 2 other parts and validate or test on the remaining. And finally, I'll train it on 2 parts and validate on the remaining. So for example, if I am training a model, let's say A0, which is a coefficient, A1 coefficient multiplied by X1 plus A2 multiplied by X2 dot 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 AN multiplied by XN. And I'm trying to relate it to Y. So what is Y? Y is the target. In this particular data set, there are 4 targets: effective porosity, Poisson's horizontal, density, Poisson's vertical, and so on. There are 26 features from the feature extraction because I've reduced the dimension. So X1, X2, dot, 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 Xn, these are the features. What I'm developing a linear model. Just for example, I'm developing a linear model because most of you know what a linear model is. It looks something like this. So what is learning? When we say machine learning, what is learning? Learning means you are trying to find out some coefficient which, when multiplied by the features, will generate the target for each sample. So what is learning? Learning means to learn the coefficients that you see here. Most of the models have some coefficient or some parameter. In data-driven world, we use the word parameter to refer to what is learned. A machine learning model learns parameters. Even before learning, what you need to define is hyperparameters. Hyperparameters are defined by us. We define hyperparameters. So for example, one hyperparameter that I defined here is use a linear model. Another hyperparameter that I defined here is instead of using 216 features, use only 26. So these are all the hyperparameters that I'm defining. And the hyperparameters that you define will control the learning. And at the end of learning, what you will get, for example, is these parameters, which when multiplied by the features will generate the target for each sample. This is what machine learning is. And in cross-validation, you only use a certain portion, a small portion of your training data. And for a given hyperparameter, you will learn the parameters. So here you will get a different set of parameters because a slightly different data compared to this. Here you will get some other set of parameters, but hyperparameter stays the same. Here you will get another set of parameters. And using those parameters, you will validate on the validation part of your data. When you validate, what you will get is memorization performance. You're getting memorization performance, and generally your memorization performance, if you're quantifying in terms of R2, coefficient of determination, your memorization performance will be higher than 90%. Once you are, so what you do is you try different hyperparameters. Sometimes you will work with lasso, sometimes you'll work with random forest. Uh, in the random forest, in a linear model, you'll use different number of coefficients, different regularization. All these are hyperparameters. So you'll try all the different hyperparameters and you'll come up with what's the best hyperparameter that will lead to the best memorization performance. And that becomes hyperparameter optimization. Once you find your best hyperparameter, you will really test it. You will generate the generalization performance on the testing folds. So I'm trying a lot of different models which have seen most of the data, most of the statistical patterns, and I'm trying to find out which is the best model out of all this. I tried ElasticNet, neural network, random forest, AdaBoost. If you don't have a lot of data, ElasticNet is the best option. There's no point in trying neural networks. I have just used it for purposes of demonstration, but I have such a small data set that neural networks are not suitable. If you want to use random forest, ensure that you don't have a lot of features. So 26 features is good enough. Don't use a lot of features. And in random forest, you are training trees, you're training decision trees in parallel. And then you are combining the results from each of the tree. You're combining as an average. In AdaBoost, you're training very simple tree. You're not training difficult trees. You're training simple trees, small trees. Actually, you know, I did a mistake here. I should have only shown you the top part. So in an AdaBoost, you're only trying small trees. You're not trying deep trees, but you're training all these trees in series. In random forest, you're training deeper trees and you're training them in parallel. And then you average the vote. In AdaBoost, you're training smaller trees and you're training these smaller trees in such a way that this tree will improve, or it will try to fix the problems in the previous tree. This tree will try to fix the problem of the previous tree. And by doing that, for each tree, As you train them in series, each tree is fixing the problem in the previous tree. And by doing that, your prediction at the end will be much better. But for AdaBoost to work, you need to ensure that you're using small trees. If you use deeper trees, it will overfit. AdaBoost will always overfit, so be careful. There's a question from Ashwarya, which is split 1 and 5 same intentionally to see the performance remains the same? Let's see. Split. Oh, okay. Uh, yeah, it's not intentionally. That's a good observation. I think there is some problem here. Just assume that this testing, let's say, is somewhere here. The testing block was selected in random, but it was selected as a continuous interval. So yeah, they look exactly the same, but I think that's a error. Somewhere, I think the fourth or fifth one is somewhere here. That's a good observation. I didn't try a lot of different models because most of the models are complex for simpler data. So ElasticNet is the best option. Random forest with very limited features is a good option. AdaBoost with very small trees is a good option. So let's look at the results. Now you have to quantify. Somebody asked me, who was that? Doni asked me, what's the rule of thumb for minimum score for generalization? Now, you need to define the score. Plenty of times people define R square, which is not a good one. R square is okay, but it's not a great uh, score to understand the performance. Mean absolute error is a pretty good one, but you also need to look at the distribution of the mean absolute error. How is it distributed for all these different samples? What's the distribution of the error? You don't want skewed mean absolute error. In this case, mean absolute error has some limitation because each target, there are 4 targets, we are predicting all the 4 targets. Each target has a different range. So I normalize mean absolute error for each of the target with range. So now I know a relative error. So I hope you understand this thing, right? So for example, if there is this is what I want to predict. And if I'm predicting something like this, then there is error. There is error in my prediction. If I just add up these errors and generate a mean, that will be mean absolute error. But if I divide it by the range in which this data is varying, then I kind of get an approximate understanding of how I perform on one target versus the other. So that's why I have mean divided by range. The other one that I use a lot is mean absolute percentage error, MAPE. It is like MAE, but before I perform the summation of the error, before I do that, what I do is I perform summation of error for each sample divided by the target. Whatever is the target for that sample, I divide it. So this is kind of a relative error. And the only problem with this particular score is if YT goes to 0, then MAPE becomes meaningless. So use it only when your target is not close to 0. But it tells you relative error. I find MAPE useful. Any questions? So this is one performance, and what I'm showing you here is performance on each split, and I'm showing you performance on testing data. There's no point in showing performance on the memorization data because memorization generally tends to be high. So what you're seeing here is testing, which was never shown to the model when the model was getting trained. And I mentioned there are 4 targets. I'm showing you performance on only one target, which is Poisson's ratio. Now, if you see here, let's look at the mean absolute error. I'm trying to predict Poisson's ratio that goes from 0.17 to 0.25 approximately. And while predicting Poisson's ratio from CT scan, I have an error, a mean absolute error of 0.009. So that's encouraging. What it means is you have an error, let's say 0.25. So there is a plus minus 0.01 uncertainty for each prediction. And this is only learned from 180 samples. Just imagine how well you can perform if you have, let's say, 180,000 samples. And that's why a lot of companies are interested in data-driven methods, because it's very easy to find that relationship. And as you give it more data, the relationship becomes meaningful, useful, and powerful. This is just based on 180 samples, which is very limited. So what you're showing here is just looking at the CT scan images, you can predict Poisson's ratio. Mean absolute error is okay, but you also need to look at relative performance. So relatively, we have a average error of 4% for each sample. Any questions on this? This is only for Poisson's ratio, which is where we performed pretty well. Now, effect of scaling. Remember, I told you that we are grouping the CT scans and CT-derived properties every 0.5 feet. So that is grouping. We grouped it every 1 feet, 1.5 feet, 3.5 feet, and so on. And the best performance came out to be when we had a groups of 0.5 feet or 1.5 feet. If we increase it, we are losing a lot of information because we are averaging everything. It's not a good idea. So for us, we chose 0.5 feet as the resolution for this task. We are grouping the CT scan, which is high resolution, every 0.5 feet after looking at this. We tried, as I mentioned, a lot of different models. If you look at neural network, it is the poorest. We don't have enough data. Neural networks will overfit the training data, and they will not perform well on the testing data. The best model in this case turned out to be simple elastic net, and Bayesian ridge regression is also a linear type of a model. It is also pretty simple. And I'm showing you Poisson's ratio. If you look at the performance of AdaBoost, Bayesian ridge regression, elastic net, random forest, and neural networks, error. The problem with neural network is we tried a lot of different architectures of neural network. None of them will work well because you don't have enough data. So the problem is the errors are high and the uncertainty is also high. So remember I showed you the 5 splits. I'm trying different train test splits. That's where this information comes useful. So this tells you how uncertain the predictions are if you change the train test split. So if you have small data, please remember, perform multiple train test split and then perform cross-validation and hyperparameter optimization on each split. So this tells you the uncertainty in the test or in the generalization, and this is very bad. It's a very high uncertainty. Best performing in this case is elastic net, a simple model. And if you compare the uncertainty, you need something which is very certain. Why? Because when you apply on the new data, you don't know what the real answer is. So you need something which is very certain to get a good, reliable, confident prediction in future. So if you look here, what's the difference between orange and red? Or sorry, orange and blue? Blue comes from CT scan images, and orange comes from CT-derived properties. Remember, I told you long time back, this service company, they gave us images, but they also gave us CT-derived properties. They have an in-house algorithm. So when they give us CT-derived properties, these are not images, these are like logs. These are high resolution data. So compared to images, we perform slightly better in terms of our certainty, in terms of confidence. We have a better confidence when we generate a model using CT-derived properties from the images. And here I'm showing you how we predict these different targets. Time right now is, let me look at the time. Time is 11:58, so we have 2 more minutes. Now, Poisson's ratio is where we perform the best. MAPE 5%, because we are comparing different targets. The best way to do it is look at the range. Some of the targets we cannot generate MAPE because the values are too small. When the values are too small, MAPE becomes biased to small values. So we are not using MAPE when the values are small. Permeability, the values can go from 0.0001 to 0.1. So it's a big range. And these are very small values, so MAPE is not useful. Effective porosity can go from 0 to 0.06. Because values are so small, MAPE is not good for these two. So the best thing to do here is to look at MAE divided by range. And with respect to range, Poisson's ratio and effective porosity can be detected at a high resolution, at a high accuracy. Rho B, which is density, can also be detected, which is very obvious. If you can detect effective porosity, you can also detect rho B. Permeability is very poor, and UCS, uniaxial compressive strength, is almost, you cannot use permeability and UCS. You cannot predict them from CT scan. That's what we are showing based on 180 samples. I think that's it. So it took us three hours total to go through this exercise. On a small data set, which I'm showing you, we did a pretty commendable job. And this thing could be done because we spent a lot of time on evaluating the model and preparing the data. Okay. So as an engineer, as a geoscientist, one thing you need to be very comfortable with is how to find features and how to reduce the dimensionality of the features. That's very important. And then what's the right metric that you will be using to evaluate the model? Okay, I'll keep shut now. Any questions, anything that you want to discuss? It's already 12 noon. If there are no questions, then it's time for me to leave.
I would like to thank Dr. Misra for taking the time and effort. It was very insightful series of presentations. And I think that everyone agrees that it was extremely useful to learn how it is the process and how it is the workflow in a data science project.
Yeah.
So thank you so much for that.
Great. And thanks a lot for
Yeah.
arranging this, and Daniel for sharing it with EAGE members.
Yeah, thank you. We also want to thank you because this topic of machine learning is a very modern topic that I'm sure in a few years will take more
More
Yeah,
relevant?
yeah,
yeah
it will be
yeah
more and
yeah
more useful, more used.
Yeah, definitely.
yeah thank you. And thank you for sharing your knowledge and your experience. I'm sure
Yeah.
that everyone that has seen us will learn a lot from you. Thank you.
Okay, and if there's a place where you can upload it, a EAGE server or something, that will be great. I don't want you to upload it on your personal server. I can do that, but if EAGE can host it, that will be great. Okay, so maybe you can do a little bit of check with Lorena and figure out, is there an option like that?
Yeah, thank you. We will check it, and I hope we can stay connected.
Yeah. Okay, you take care.
Okay, thank you so much. Thank you so much,
Bye-bye.
Daniel.
No, thank you so much, Kay. Thank you so much, Dr. Misra.
Yeah, take care.